session video 2. So in this video, we are exploring how machine learning and neural network and deep learning models can be applied to IoT data, like temperature readings and image classification tasks. This is a hands-on session, so you will see the code examples and learn how to build, evaluate, and deploy models. So first, we need to check the files from our course content in Blackboard. So we will have some data sets about like we are using two cargo data sets, one for IoT temperature reading, and another is for cat versus dog images. So for the temperature data, so you will see like this, like a CSV file. So this is the 1 day's temperature series, and for the cat and dog, it's like a cat and dog data set, and we will have trend set and test set, and we will have dog pictures and cat picture like this. So they are all on the Blackboard content, so you can download it here. So now let's focus on our first lab mission is about machine learning. So first, I would also suggest you to use a Jupyter Notebook to deploy our model, and we will use this to show the code step by step. So first, we need to import the necessary libraries. Some of them you are very familiar with. So we use Python libraries like pandas for data handling, scikit-learn for machine learning, and TensorFlow and Keras for uh, the neural network and deep learning. So first, ensure you download the dataset, and the first lab Python, we will need to use the kinetic temperature data. This dataset represents the time series data temperatures from the Internet of Things sensors, as it is sequential and often requires forecasting, like predicting the future temperature. So this is also this lab's tasks. Later, we will compare this with the image data, and where processing the steps differ entirely. The first, read the CSV. If you just put your CSV file in the same folder of the code, so you can read this just like this. If you are not, you need to write a path here to help the code to read your dataset. So first we need to see the data set preview and check if there are any missing value. So then we will need to visualize the data. So visualization helps spot the trends. Plotting temperature over time might reveal the pattern and anomalies. For example, if some temperatures reading are missing, we can fill them with the means or constant. You have learned how to deal with missing value on the lecture 2, right? So it's like to do the imputation. So next we show the picture of the temperature. And if your temperature X label is about that, so if your date looks like this, you can use the automatically adjust the tick location and to rotate the X label and align the right for the better visuality, and automatically adjust the subplot parameter for the better fit. So you can add this point to make your plot look clearly, and So this is about the visualization. And next is about to uh, extract the feature and then add the lagged feature. So what is the lagged feature? So lagged feature are a powerful tool in time series analysis and predictive modeling. They involve using the past value of a variable. For example, in here is the temperature to predict its future values. So here, you can see that the yesterday's temperatures will highly influence the today's temperature. So the lagged feature will model these dependencies. And here we need to drop the non-value. So as the first two rows, they have no previous temperatures. So then encoding the out-in status and scale the features. So last time, some students are confused about the scaling. So here I make some explanations. So scaling ensures features contribute equally to the model. We will use a standard scaler here, and it will standardize your data by transforming it to have a mean of 0 and a standard deviation of 1. For more details, you can just put your point here and see its original formula, function formula here. And you can see that it's just to do the standardized function to make your data has the mean of to 0 and the standard deviation of 1. So for more detail, you can refer to the online official document. So feature scaling is the technique used to normalize and standardize the range of features in your dataset. In simple terms, it adjusts the value for all features to a common scale so that no single feature dominates the others. So in here, for example, we have like the two features here. We say the hours and the month. So hour ranges from 0 to 24, and the month ranges from 1 to 12. So if we don't do the scaling, uh, the model will might give the more importance to the hours. So just because its value are bigger. So scaling ensures that all the features are contributed equally to the model. So key insight here is that the clean data is the foundation of the good model. Missing values or unnormalized features can mislead your models. So then we move to we just build a simple linear regression models. We will predict the future temperature using the historical data. First, we split the dataset to the train and the test set. And then initialize and train the models. The model we use here is called decision tree regressor. So also you can point here and see its details. So I will just simply describe it. And it is a machine learning model from the scikit-learn library in Python. And is used for the regression tasks where the goal is to predict continuous target variables. For example, here is the temperature, and you can also use it to predict the price or something. So the model works by splitting the data into smaller subsets based on the feature values, creating a tree-like structures of decisions. And each leaf in the tree represents the predictive values. For more details, I would suggest you to refer to the documents of scikit-learn. So like this, in this decision tree regression document, you can see all the contributes and the functions here. Now, after we build and train the model, we make the predictions and evaluate the model with the root mean squared errors. So the root mean square error is the square root of the average squared difference between the predicted value and the actual value. It can summarize the average magnitude of the prediction errors. So here our root mean square error is 6.4, and it is quite large because as we can see, our temperature is range from like 15 to 30, and if we make the error about six degrees Celsius, it may maybe not so accurate, maybe so accurately. So as I said, this is just a sample of example of building a linear regression model. So if you want to make your model have the better performance, you may need to modify its configuration to take its hyperparameters. Now we move to step 3, the model deployment simulation. So why this matters? So as our course is called the Internet of Things, the linear regression is interpretable and fast. So imagine that we need to deploy our model in the real world situations on the sensors or on some devices. So the first we need to consider is about the real-time predictions. Uh, and so we need our model to be the lightweight, as the devices may have limited resources for the fast computing, and we need to monitor its performance to catch the drift and regularly update the model. So we have some discussion about to deploy the models on the Internet of Things devices to make the real-time predictions. Now we move to the next part of our lab, design a neural network. So first, we also need to import the necessary packages for the neural network building. So many of them are familiar to you, as the last lab session you have imported them. But here I need to introduce the Nego package for you. And the Nego package here is for us to build a spiking neural network. And its dependencies only requires packages NumPy version is up newer than 1.1619. So here we can see when we install the Nego on your environment, you can see the requirement already specifies as our NumPy is version is newer than 1.19. At that time, my NumPy version is 2.0.2, and that's satisfied. However, if you just use a NumPy 2.0.2, you may miss the error that some functions in the newer version of NumPy is missing, as it's updated and deletes some functions. So if I remember rightly, one is called the product. As you may see, the arrow reminds you the missing value. So here we suggest you to uninstall the NumPy and install the NumPy in the specific version, which is 1.26.0. So this on my PC, I installed the NumPy version 1.26 is fine. It's fine, and it will go well. So after we import all these packages, we can start to generate the dataset. So now we generate a synthetic dataset for the Internet of Things data, and with 1,000 samples. So here the result temperature series will look like a waving line. from the sine function and has some fluctuations, small fluctuation from the noise, random noise here. So this is what we generate the data set. So just like the last lab session, we have the temperature, we have time, we have the motion 0 or 1. And then we do the data processing. As the data is from our generation, so we may not need to data cleaning, but this is the necessary part of data processing if you use the real world data set, as they may have some missing values. So now we first visualize the data we generate. So as I said, it's like the waving line as a sign and has some fluctuation with some noise. And then we also need to normalize it using the mini-max scalar. As I said, you can point on here and see what is the mini-max scalar and see its difference from the standardized scalar. So so it is another way to scale the data and normalize it to the range from 0 to 1. And then select the feature and split the data to the training and testing set. And now we need to reshape the data for convolutional neural network and recurrent neural network. So here, even you say the function is the same, but it's different for convolutional neural network and for recurrent neural network. So here, we're using the convolutional neural network and the recurrent neural networks. The input data needs to be in a specific shape so that the model can process it correctly. The reshape operation here looks the same, but it's very different. So the CNNs are typically used for image data and expect the input data to have the specific dimensional structure, such as the batch size and height and width and channel, like that. It expects the input with some height, width, and channels. So the code here means that each data point is treated as a one by one image, one by one image. So its height is 1 and its width is 1. So it's often used for simple CNN models dealing with the one-dimensional dataset or time series data. So here, as our dataset is temperature, so it will define as the one by one dimensional dataset. As for the recurrent neural network, RNN, are used for the sequence data and expect the input data in the format of bench size, time steps, and the features. So its code means that each data point is treated as a sequence with the time step of one and one feature. One time step and one feature. So this format is suitable for the simple one-dimensional time series data. So here the -1 means that this code will automatically calculate the batch size, which is the total number of samples in the data. So the -1 means it automatically calculates the batch size. So after we build do the data processing, we first build a deep neural network. So we use a sequential to build it, and the network is composed of several layers, each with some specific rules. So the first layer is the dense layer with 10 neurons, and use the activation function called ReLU. So what is the dense layer and what is ReLU? You can relu activation function, and I will explain it later. And here the layer takes the input data. You need to know that the layer here takes the input data and begins the process of learning patterns. And the input shape is determined by the number of features in our training data. So the next layer is also a dense layer, but with a less neural network, which is 5, and the activation function is also ReLU. So this layer further processes the information from the first layer and helping the network to learn more complex patterns. And the last layer is also a dense layer, but with only one neurons, so which use the sigmoid activations. So function, this layer is designed for the binary classification task, means it outputs only outputs the value between 1 and 0 and 1, which can be interpreted as the probability of belonging to a certain classes, which is in here is here is a motion 0 and 1. So then we train the model to do the training. Here we can see that the we set that epoch is 15, and so now I would like to introduce a little about what is an epoch. So an epoch is a complete pass through the entire training dataset during the during the training. For example, here we generated 1,000 samples, and then we split the data set to training and testing, and the testing set is size is 0.2, which means that 200 of the data set is for test. So the training data set remains 800 samples. So now in the training process, we use 0.20% of them as the validation set. So the actual training data set is like the 800 multiply the 0.8, which is 640, which is 640. So, and the batch size is 10, which means each batch contains 10 samples. So we need for 640 data samples, we need 64 iterations to go through all the data set. So in one apple here, we need to go 64 iterations to go through one apple. So this is apple. And now we introduce what is batch size. So batch size is a very important parameters in machine learning. So, and it will affect the performance. Here we use the batch size is 10, means that we have 10 samples in one batch size. The model performs forward propagations on these 10 samples to compute the predicted values for each sample, and then calculates the loss for each of these 10 samples. For example, using the mean squared errors, and here we use the binary cross entrances to compute the 10 samples losses. So the loss value of these 10 samples are averaged to obtain the average loss value. And this average loss value is used for backward propagation to compute the gradients. So the model parameters can be updated based on the averaged losses and with these computed gradients. So this will help to stabilize the gradient updates by reducing the impact of outliers. So if we have a large batch size, for example, if we have 100 batch size, which means more samples will, in one iteration, using more data for each updates, and it will result in the gradient estimate that closer to the trend true gradient. So if the batch size is a whole data set, so in one iteration it will conclude all the data sets, all the data, and will more closer to the true gradients. However, the large batch size needs more memory to store the data, which may lead to the memory shortage, and also it will have the risk of overfitting. So you may think about what the influence will have by using a smaller batch size, and the balance of the batch size is the art in the machine learning process. So another thing I need to explain here is the callbacks. In the context of training a neural network, using a framework like curls. So the callback parameters, which we import here, curls callback, we import the early stopping here, and it is a powerful tool to help you to monitor the training process. So the early stopping is one of the most common callbacks, which will monitor the specific metrics. Here we said that it monitors the validation losses and stop training if it doesn't improve for a certain number of epochs. So this will help prevent the overfitting and saves time by stopping the training process once the model has converged. So in here, after five epoch, if the model's accuracy does not improve, it will stop. So the patience is fine. So here we can see that it is stopped at a very early time. So now we can build convolutional neural networks. So convolutional neural networks different from the previous network is that it uses the convolutional layer, and these are designed to process grid-like data such as images. They use convolutional layers to automatically and adaptively learn special features from input data. So CNNs are like particularly effective for image recognition and classification tasks due to their ability to capture spatial and temporal dependencies in images through the use of filters. So the convolutional layer we use here is convolutional one dimension, as our data input data is one dimension. So we use 16 filters, and the kernel size is 1, and the activation function is ReLU. So it remains just the same as the deep learning neural network learning. So we put the shape as one by one imaging here. So also we train it. And next, we will build a recurrent neural networks. And the recurrent neural networks are designed to handle sequential data by maintaining a memory of previous inputs. They are particularly useful for tasks where context or orders is important, such as language modeling and the time series predictions. So as we predict, the recurrent neural network would be suitable for the temperature predictions. So it uses the LSTM layer. So what is LSTM? It's called long short-term memory layer. So the long short-term memory means that it's designed to capture the temporal dependencies in sequential data, just like the we call lagged features. So it will recall the sequential of the sequence of the data, makes them suitable for the task for the time series predictions. So in our settings, it has 10 neurons. The shape of the input data is sequence of length 1 with 1 features per time step. So here it will also have a dropout layer. So the dropout layer is a regulation technique to use to prevent overfitting by randomly drop out some input. So what it means? It means that randomly setting a fractions. So here is 20% in this case of the input unit to zero at each update during the training. So this will help the model generalize better by reducing its reliance on the specific neurons. But then we also train it. So as we can see, that after we train all these 3 models, we evaluate the models with this accuracy. And we can see that our DNN got the test accuracy at 47, and the CNN got the 45, and RN got 15.2. As we predict, the recurrent neural network is kind of more suitable for the time series predictions, as here is temperature prediction. So we can also plot the training history. So as we use the early stop strategy callbacks, so we only see the several apples in the training history. As we can see that they are differ from their stop is different from each other. So next we will simulate the prediction for the spiking neural network. So spiking neural networks mimics biological brains using pulse and timing instead of continuous values. So it calls spikes means that the neurons only fires when the inputs reach the threshold, and it's good for the temporal patterns recognition and energy efficiency, which is suitable for the Internet of Things situation. So we use Nego to build a spiking neural network. Now here I will explain the code to you, and its threshold is 0.5, as it means that activity exceeds the 0.5, it output 1, and if not, it's output 0. This results in binary output, so you should expect the plot point to be around 0 or 1. So I mean, this is just an example of the spiking neural network. If you want to make it more like the real world situation, you need to make modify its configurations, like the input node. As here we use the input deck is just the simple linear space from 0 to 1 with 100 values. You can use it as a test venue. And also here, the synapse settings. So the synapse settings, if we uh, to achieve more varied outputs from the spiking neural network, you may consider adjusting the number of neurons, the synapse time constant. The synapse time constant makes the input of the spiking neural network become decrease. So the smaller the value is, uh, the smoother the input is, and it's closer to the continuous input. And all the functions used for connect to the output function to connect to the output node. It's also important to ensure that the input data to the spiking neural network is also diverse enough to produce different output. So here I can show you if we change the input data to the text value, and we can see the sort is quite different. As we can see, some of them are clustered in around the 0, and some of them are clustering around 1. So will be more like in the real world setting. So about the questions, for the neural network settings, the as the training accuracy stop different in the random different epochs. Why so random epochs? So it's called here. So why this different neural network stop at different epochs? So it may because the neural network validations, as we can see, our callback is based on the validation loss. If the validation loss does not improve, it will stop. So the neural network validation loss may fluctuate greatly during the training, and takes longer to trigger a stop, or takes shorter to trigger a stop. Secondly, the difference in the model structure and optimizing process will affect the training dynamics. For example, the deep neural network may be more susceptible to overfitting and causing the validation accuracy to stop improving quickly, while the convolutional neural network may not stop until the more epoch due to the filter extraction capability of the convolutional layer. So in addition, the hyperparameters such as learning rate and batch size can also affect the training speed and the convergence. Okay, so here are all these 4 neural networks, and I would like to suggest you to modify its configuration, to change its epoch, to change its batch size, and to change its threshold, and so on, and to explore it by yourself on the lab session or anytime you want. So now we move to our final Python file, as we need to build a deep learning model here. Also, we need to import these libraries, and first to download the dataset to the code. So here we need to update our dataset path. So my dataset path is in here, and if you directly copy the path on Windows, and is use backslash, so it will use backslash. So you may need to change to the forward slash as in the Python to read it correctly. And then we do the data processing. And here we have the new things called the data augmentation. So why we need data augmentation here? So data augmentation means that we use this to generate batch of tensor image data, to generate some tensor image data with real-time data augmentations. These parameters are used to augment the training dataset, which can help to improve the robustness and the generalization of the model by exposing it to the wider variety of the imaging conditions. So this is just a tool to help us to make our data become more generalization and become more robustness. So if you want to know more about the image data generated details, I suggest you to refer to the official documents to see how it generates some real world augmentations. So now we build a deep learning models with transfer learning. So here we use a base model. The base model is a pre-trained model called mobile net version 2, using the weights trained on the ImageNet dataset. But we set the include top as false, which means that the top layer, which is the final fully connected layer, is not included. Allow the mobile net version 2 to be used as the feature extractor. So the top layer we can adjust by ourselves, add by ourselves. And the input set is setting as 224, 224 and 3, which means the input imagery is set to 224 by 224 pixels with 3 channels of color, which means the RGB, red, green, and blue. So in the sequential functions, we first add the bed model and as a pooling layer, and then as a dropout layer as a density output layer for the binary classification. So here we need to freeze the base model layer. So we do not want to train the base model, and we just want to train our global pooling other layers. Then we use another callback function called the model checkpoint. So the model checkpoint help you to save the model parameters in the training processes. So here we said is always save the best model parameters with the least validation loss, and save best only is true. So it's another powerful tool of callbacks, same as early stop. So we train the model now, and as is a deep neural network, it may cost a long time to complete the training. As here, every iteration is 17 So after that, we will evaluate the module with its accuracy and plot the training history to see if it's overfitting or not. So let's wait for its training. So we can see in the image classification tasks, the convolutional neural network is really have a good performance as its accuracy usually got to 19, even 98, I guess, in some small data set of classification tasks. So that is really suitable for the classification task. So now we complete the uh, training and to see our model's performance in the test. So we got the accuracy like 93%, which is quite good, quite good. And we can see its training process. So we can see its training accuracy and validation accuracy is quite the same, and the loss is decreasing by the epochs. So which means is training that is not overfit, which is good. And now we move to the model deployment discussion. So the keyword here is also one is real time, another is the device resources constraint. So we need to make our model become more efficiency as the devices in the Internet of Things situation may be not so powerful, and their computing resources constraint uh, is limited. It's limited. So now we have the optional steps, the fine tuning the model. So here what is the fine tuning? So after we get a base model, if we wanted to get a better performance on some other downstream tasks, we may need additional data to train it by unfreezing some or all of the layers of the base model and retraining them on our specific dataset. This process allows the model to adjust the pre-trained weights, slightly better fit the new data, and potentially improve the performance. So here we can unfreeze the base model. So we train all the layer of the base model and to see its performance. And we also only train it like 10 Apple, not like this, like when the 20 Apple will have the short time. Will have short time. So as I'm recording uh, recording the video, so my GPU performance uh, will be limited, so it has a smaller time. So if you are doing it on your own PC, I guess it will not be so slow like this. So this is optional steps, and we can see its performers also do the same as the last step, and we can see its training history. Okay, last apple. Okay, okay. See its test accuracy actually a little bit lower than the first model we trained. So what happened? You can see from the plot. So we can see that the model accuracy in the training accuracy is higher and higher. However, the validation accuracy is low. So which means it's overfit. So overfit means that the model just remember all the results in the training data set. And when it's fed to the data set, like the test data, it didn't know, it will have uh, have a bad performance, have a bad performance. So this is called overfit. So we can see from is uh, so now is the all of these videos. Today we have built like the one machine learning model, linear regression, simple linear regression model, and four neural network model, deep neural network model, convolutional neural network, and recurrent neural network, and spiking neural network. And finally, we do a deep learning model. So we like build 6 models of the Internet of Things for the temperature prediction and the image classification. So it's quite a lot. So in your experiments, remember, pre-processing is critical. So garbage in, garbage out. So choose the model based on the data type. As you can see in the temperature prediction, the recurrent neural network performs better, and in the classification of the image, the convolutional neural network performs better. So choose models wisely. And then the experiment to make your hand dirty to tweak the hyperparameters like the epochs, layers, and learning rate to see how this hyperparameter change the model performance. And thank you. This is the end of this video.